Hi folks, this is AP Chemistry and you're here with Miss Gray. This is Unit 6, podcast number 4, which I decided to only record a portion of because all of the other information in this podcast you can find on my general chemistry website under Bohr, Aufbau, and electron configurations. So review what you need to review so that you can do Bohr diagrams and Aufbau diagrams perfectly every single time, and so that you can write electron configurations both in the longhand and in the shorthand. But this that we're going to do now is the part of the podcasts that's not in general chemistry. So I'm going to get us a blank screen so that we can look at an Aufbau diagram, and then we're going to have to go back to this other one. So let's go with a black screen this time. And we're going to look at the Aufbau diagrams for two different elements. First, let's start with gosh, I don't know. Let's look at nickel. That's a good one to work on. So nickel starts with 1s, just as everything else, and then fills in the 2s, and then 2p. Then comes 3s with 2 electrons, and 3p. And then after the 4s comes the 3d. So we gotta put the 3d over here. 5 spaces for 5 different orbitals. So 3d has 5 spaces. And nickel fills up 8 of those. 1, 2, 3, 4, 5, 6, 7, 8. So I want to talk to you about magnetism. You see, for an element to be magnetic, then we have to have what's called paramagnetism. Paramagnetism refers to a condition in which the orbitals do not have all the electrons going the same way. So orbitals do not have paired electrons, and thus they're more influenced by the presence of a magnetic field. So orbitals do not have electrons all paired up. So here you can see nickel has these 2 spots where there's no partner for these electrons. So nickel may have more magnetic qualities than, say, something like zinc. Zinc has 2 more electrons than nickel, so we would fill in these spots. And so zinc has everything completely paired. That's the situation called diamagnetic. These types of elements are not greatly influenced by a magnetic field because all electrons in that subshell are already paired up. Okay, now let's look at iron. So we have 1s is full, 2s is full, and then comes 2p. And then of course comes the 3s and the 3p. And I'm going to run out of space. I can already see. After the 4s comes the 3d. So I'm going to scooch that over here. 1, 2, 3, 4, 5 for my 3d. So let's fill in for iron. 1, 2, 3, 4, 5, 6. So which element do you think would have the most magnetic properties? Would it be, first we had in green, nickel, and then we had here zinc that was all paired up, and then this one is iron, where only one thing is paired up. Right, iron has the most magnetic properties because of the abundance of unpaired electrons in this D subshell. So it's considered to be paramagnetic since not all of its electrons are filled up. Oh, gotta get rid of my black screen. So let's come back to this spot and we'll fill this blanks in. You've got this in your notes where you have your Aufbau diagram, so go to the page in your packet where you have your Aufbau diagram laid out for you. Right next to that you'll find these parts of your notes to fill in. So diamagnetism is a condition where the elements have all electrons in that suborbital spin paired. So maybe not all of them in level 2, but all of them in the 2p, or all of them in the 3d are all paired up. So that would be diamagnetism. Paramagnetism are elements that do not have their electrons spin paired. So these elements would be more strongly affected by the presence of a magnetic field. So I needed you, of course, to know how can we tell if a substance is going to be magnetic or not. Now let's look at some of the exceptions. I know that you've got your patterns down. You know which patterns to follow for which substances, for 1s, 2s, and so on. But there's some exceptions that I want you to know about. Look at this pattern that we have here. For scandium, that's the first place that we fill in a d orbital. So scandium would be right here. Argon is our shortcut. Then we get 4s2, 3d1. Then titanium is right next to it, 4s2, 3d2. And then vanadium, 4s2, 3d3. And then where did my next one go? How come I don't have a 3d4? Well, look what happens here. Here's my 4s. And then I'm going to put my 3D right here. 1, 2, 3, 4, 5. So chromium would normally look like this. 4s and then 3D, 4. But see, what chromium does as an exception is that it kicks an electron out of the s and moves it, promotes it to the 3D orbital. And here's why. A half-filled shell would be more stable than one that's lacking just one electron. It's so much more stable, in fact, that the cost of moving this electron out of the 4s is regained in the end by putting it into a more stable position in the 3D. Now for vanadium, vanadium looks like this. We have 4s and then 3D. 1, 2, 3, 4, 5. So we fill in the 4s and then have 3D, 3. So look, we have 2 electrons that we're shy. So the cost of moving 2 electrons into the D would simply be too great. It's not worth it. We don't gain enough in the end. So vanadium doesn't do anything weird, but chromium kicks one out of the S and puts it into the D every single time. And it's not just chromium, but the entire chromium family. So molybdenum and tungsten and seaborgium would all arrange their electrons the same way that chromium does, taking one out of that s orbital and promoting it to the d orbital to improve the stability of the entire structure. And that's not the only one that does. Let's look at another exception. We have copper listed here as an exception. So here's 4s for copper, and then 3D, 1, 2, 3, 4, 5. Of course, this isn't where the 3D goes. We would have a big space for the P, but we just want to zoom in on just these electrons. Here's what copper would normally look like. We would have 9 electrons filling in the d orbital space because it's 9 steps across to get it to copper. So notice right here, if we had just one more electron, then this suborbital, this 3D, would be completely filled. And that would improve the stability of the entire structure for copper. And the stability improves by so much that it's worth the cost of taking the electron from the 4s and putting it into the 3D. So look what happens in the configuration of copper. Move an electron from the 4s, put it in the 3D, so the 3D is all the way full, and we gain enough stability to justify the expense, energetically speaking, the expense of moving that electron. So there are some exceptions in the d orbital, the chromium family and the copper family. So copper, silver, and gold all act in the same way. They all do this with their electrons, so I need you to be aware of those. In the f orbital, there are more exceptions, other things that will do this as well, because of the same reason in the f block. Remember, f has, so let's say 6s is full, and then we have the f orbitals to fill up. 1, 2, 3, 4, 5, 6, 7. So here's our 4f. And so what lanthanum does, rather than sticking this one electron into the 4f, puts it in the 5d. Kind of weird, huh? 5d fills before the 4f, but then we don't put 2 electrons into the 5d. We put one in the 5d and one in the 4f for cerium. That's a crazy looking exception. Then promethium is finally now we're getting away from the d orbitals and putting them into the f orbitals where they're supposed to be. So I know these exceptions seem a little bit crazy and we don't quite understand them, but the only ones I need you to know are the copper family and the chromium family, and then be aware that there are some also in the f orbitals that you don't have to remember. You just treat them as if they do what they're normally supposed to do. But here's the exceptions in the f block. There's probably more, but these are kind of the big ones. So lanthanum, cerium, promethium, gadolinium, and lutetium, those guys act kind of funny because look, here's a half-filled orbital. If we can get a half-filled orbital for these guys, or a completely filled suborbital, then we'd be a lot more stable. So we move things around so that we can achieve the most stability for the arrangement of electrons in the atom. That's all there is to it. Stability equals happiness. Okay, guys, I'm going to see you in class. We're going to practice this, and you're going to become experts.